So I want to explain a little bit about what this talk was supposed to be and how it's going to work out, because there's been some changes in plans. So Wayne and Dinesh wanted to have a sort of a panel discussion about Tate's time at UT. And so he asked me and David Saltman and Fernando Rodrigues-Villegas to be here and have this panel discussion. And unfortunately, Fernando had to pull out a couple of months ago, and then at the last minute, David also pulled out. So I just learned yesterday that I'm alone. But fortunately, Cristian Popescu and Barry Mazur have offered to share also some memories about John. So what I'm going to do is I'm going to talk a little bit about John's time at UT and a few things more sort of on my side, so it'll be more personal memories, and then I'll pass it on to them, and they can speak about that. So this picture, everybody likes. This is a very nice picture. This picture was taken at the University of Texas, and in fact, if you look at what's written on the blackboard is a product formula. So where is Dustin? There it is. All right. So, but it's not John's handwriting. It's Jeff Valler's handwriting, and this is Jeff Valler's blackboard. So they came to Texas, I think, in 1989 or 1990. 90. So I wasn't there, and so I would have loved to have David Saltman here explain to you the details of how he got hired. But he came with the intention of building a group and creating an environment in number theory. There were a couple of number theorists there and a couple of algebraists the algebraists were people that John was working with, David and Bill Shelter, and a couple of number theorists, Jeff Valler and Frank Girth. So, and John set out to build a group, and I was very fortunate to be offered a job there in 1992, and so I got invited to go to an interview by John Tate, and it's like, how can I possibly refuse that? And so I was very fortunate to go there and spend 20 years working with him there. I was at UT for 25 years, but John was there for 20 years. And so we created a group. Jeff Valler was also part of the group. And then we hired Fernando, who should have been here but isn't. And the four of us kind of built together this very nice environment. And we had always postdocs. So Cristian is one of the postdocs, and so he'll be able to tell you a little bit about that. We had graduate students. So I wrote a few things about this, and then I was reading through them, and I thought, well, this is kind of mundane. We had postdocs, we had graduate students, we had a seminar. But, it was wonderful because, it was a really sort of nice environment, and John created this friendly environment that everybody could participate and be valued, and it was great. We had lunch every day and all of that. So the grad students, we had a ton of grad students, and there's at least one former grad student from UT here. But John only had 2 graduate students at UT, and then I think he felt that maybe having a graduate student at UT was a little different from having a graduate student at Harvard, and that he would rather leave it to the rest of the group to run the graduate program. But he was very helpful to the graduate students, even our graduate students. So I wanted to mention a couple of situations where he helped 2 students of mine. One was Francisco Portillo, who was working on the Mazur-Tate refined Burstyn diet that he talked about, and doing some computation. So in the paper of Mazur and Tate, you have one curve, and you do like 100 primes or something like that. And so I said, well, you have to do more curves and more primes and see what. But so he did, and there was some subtle point because, some sum of modular symbols comes out to be a very elementary invariant in most cases, but sometimes there's some extra divisibility, then there's a jump, and so he got caught up with that, and John was very helpful in figuring out exactly what was going on. And of course, the statement of the conjecture was correct, but it took a little bit of effort to figure out what was wrong with the interpretation and the code that was mismatching, but eventually we got to that. And the second student that I had that John had a lot of involvement with was Luis Finotti, and Finotti was doing some computations with finding lifts mod p squared of curves in characteristic p, and he found, and he was interested in the degree of a function, and numerically the degree of a function was always one less than the bound that he had, and there was so there was a coefficient that was always vanishing, and he couldn't explain that, and eventually we finished his thesis and like that, and he talked to John, and at some point, John figured out what was happening, and he wrote a little paper, which is called On a Question of Finotti, and I think the student must have been in heaven, right? Because there's this published article by John Tate called On a Question of Finotti. Let me see what else. I had a lot of things written out. Yeah, so one thing about the seminar is that we had this weekly seminar, and it was partly funded by John's endowment, the endowment of his chair. And we had this joke that there was the Tate index of a talk, which was how many minutes would it take for somebody to mention Tate's name in the talk? So it was usually finite, and that was good. But here, of course, the index of all the talks is 0, right? So that's very good. So yeah, I want to talk about, so one thing that I really wanted to talk about is this paper we wrote together. And so there's an interesting story connected with the paper. And I sort of wanted to talk about the paper because I wanted to tell the story. And I wanted to tell the story because I wanted to talk about the paper. So you guys figure out which way the motivation goes. But let me tell you the story first. So we're working on this, and it's moving along. We're writing things, and there was a few things that we wanted to organize. But at some point, the paper was nearly complete and all that. But then we hit the point where John starts to obsess about how the paper is written, right? And so, oh no, we have to do this more carefully, or we have to extend this, and then he sort of starts writing notes and not sharing them, and holding back. And I thought the paper was finished. We had proved the theorem. It was nice, and okay, let's do this. Okay. It wasn't moving. I was about to go on a trip, so I didn't want to press the issue then, but I was thinking maybe when I come back from my trip, I'll work on John. And then, so it was a Thursday, so the dates are somewhat relevant. I came into work, and I went to talk to John, and it turns out he had an exam. The doctor wanted to take an X-ray of his abdomen, and something funny showed up on this X-ray. And he was very concerned. Some of you may know the story. I don't know how many people know the story, but it has a happy ending. So, but at that point, he was very concerned, and the doctor wasn't sure what it was. And they made an appointment to go to Houston, to the MD Anderson Cancer Center, to have a better look at what was happening there. And he was going to go on Friday. So I was talking to him. He was explaining this to me, and I said, I hope everything goes well, and so on. And I said, don't worry about the paper. We figure that out later. And he said, no, but I'm worried. But I think I need to fix a few things. And okay, so I wish him best of luck. I was going to travel on the Saturday, so I wasn't going to see him for a while. So I left to go home, and he was still at work, and he usually worked late. He was very conscientious, even though, he could afford to relax if he wanted to. So I came to work on Friday morning, opened the door of my office, and there was an envelope under the door. And what it was John's notes. And he had left a message saying, I've worked out all the things I've worked out. Here it is. I want you to have that. Maybe he was worried he wasn't, I don't know. He was busy in Houston, and I don't know. So, okay. So I looked through the notes. It looked fine, and I put them in my briefcase and went on my trip on Saturday. I went to Oberwolfach, and I got there on Sunday, and I was jet-lagged. So I was awake for 3 nights, sort of, like at 3 in the morning I would wake up. And so I would go, this was in the 90s, so those of you who are old enough to remember this, there was, we didn't have Wi-Fi, we didn't have, laptops, so we had to, if we wanted to use a computer, we had to go to a computer lab, and the computers were all named after the train stations on the way to Oberwolfach. And so I sat down in one of those workstations, and at 3 a.m., I started typing up the paper. Tech was a thing, was beginning to be a thing, and but the paper was mostly handwritten notes, but I started typing it up. And I did, I had enough of those sleepless nights that I finished typing the paper and uploaded it and came back. And next week, Monday of the following week, I was back. And John was there, and he said, well, it was nothing. There was a shadow behind my pancreas that the doctor was very worried about, but it was just a fold of my intestines, and the doctor said, you have nothing, you can go home. And great, wonderful. It's the best news ever, Happy to hear that. And I said, yeah, and I was typing up the paper in Oberwolfach, and he said, oh, yeah, but I think lemma 3, we need to... No. I'm not giving it back to you. I am sending it to the journal tomorrow, and you won't have a chance to look at it again. So it got published, and I want to talk about the paper. So Dustin said something about a less well-known work of Tate. This is even lesser well-known, but it got the name. It wasn't me who gave it the name. There it is. Okay, so this goes forward, or this goes back. Okay, so I want to talk about the Tate-Voloch conjecture. Somebody gave this name. There's a conjecture in the paper. So we proved the theorem. So I'll state the conjecture and mention the theorem. So the conjecture is that if you have a field with a non-Archimedean absolute value and an abelian variety defined over this field, or a semi-abelian variety defined over this field, and you have a closed variety x of A, then there's a lower bound for the distance of torsion points on A, not in x to x. So the torsion points is this cloud of points, and you have the subvariety there. And the torsion points are either, some torsion points might be in x, but if they're not in x, they're a certain fixed distance away from x, so they cannot accumulate into x. And I'm not assuming anything about the field being locally compact or anything, so you could have sequences of points converging to x without converging to a point in x. So this is a strengthening of the fact that the torsion points form a discrete set, which is one consequence of this. This is an easy case that you can prove that is discrete, but the discreteness manifests itself in this algebraic way. So torsion points cannot accumulate to to subvarieties. And we proved this conjecture in the case that A is a torus, so a product of GMs, in the case of K equals CP. So that was the paper that we wrote. And so there's two cases that, I mean, the proof naturally splits into two situations. There's the unramified, so the prime to P, so if you're working in CP, the prime to P torsion points and the P power torsion points. And the prime to P is easy. And in fact, John gave a very, very slick, two-line proof of the case of prime to P. I had a more complicated thing that I was trying to compute some equations, but he said, if you can reduce to the case of a hypersurface and even a linear hypersurface. So you have a sum AI xi equals 0 is a hypersurface, and maybe you write this as Vict vector. So the AIs are going to be AI0, AI1, etc. And you want to evaluate this at roots of unity because the torsion point. So you want to measure how close to the subvariety is the torsion point. So you put the root of unity here. This goes on forever. And you want to see how close this is to 0. But this can be written as F0 of zeta 1, etc., F1 of zeta 1, etc. So there's some polynomials. So if you write this as Witt vectors, you get some polynomials there. And John's observation was, these equations is by Noetherian induction, either you have a point that satisfies all the equations, or there's a finite set, up to a point. You cannot have infinitely vanishing, right? So if finitely many of them vanishes, all of them vanishes. And so you get that, this place where it stops is P to the minus, that index is the distance. So that was the proof on the prime to P phase. So prime to P, because we're looking at Teichmüller lifts of elements in characteristic P, so that's the proof of the unramified case, which is the prime to P case. But the P part was the part that we had to work quite a bit more. All right. I want to mention some, not in any detail, but a few things that are known. So the conjecture itself for abelian varieties, or maybe for semi-abelian varieties, was proved when K is QP bar. So we were a bit optimistic and stated the conjecture with abelian varieties defined over CP or any. We don't know what, if the abelian variety is not defined over QP bar, we really don't know what's going on. So this is still open. But if the abelian variety is defined over QP bar, Tom Scanlon proved this theorem. And then, so that sort of, the original question was kind of more or less settled, not entirely, but for the most important cases. But what it turned out is that there are analogs of this question where you replace torsion points, or you replace the abelian variety by something else, and replace torsion points by something else. So one thing that people looked at is Shimura varieties, or Shimura varieties, which are moduli spaces of abelian varieties with some additional structure. You can talk about CM points. And the CM points have sort of the same properties as torsion points in some ways. And so you can formulate this question, in this context, so subvarieties of Shimura varieties and torsion points replaced by CM points. And there's been some result. I don't think the full statement is proved, but there's many nice results proved by Felipe Habegger and King Liu. And there's other ways you can change it. So a student of mine, who Tate also helped quite a bit, Anna Nera, wrote a thesis where she looked at the case where you go back to the original case that we dealt with the torus, but instead of looking at algebraic subvarieties, we looked at analytic subvarieties, so things defined by convergent power series. And so she was able to prove a version of this thing. So some of that argument extends, so there's already something you can start with. but then it was pushed a little bit further. And then Vlad Serban, a few years later, came to this question by a very different route, and had some sort of further results in that direction. And more recently, there's been several papers where, this is an idea that there's been a while, that periodic points of dynamical systems are like torsion points of abelian varieties. In arithmetic dynamics, one studies there, and then you can sort of set up the same kind of question, and there's been progress in there by all these people there. Like I said, I really was talking about this to be able to tell the story. Maybe I'll tell the story to be able to talk about this. I don't know. Let me just end with a picture of us at a restaurant called Las Manitas that unfortunately closed. It was in Austin. Mike Artin used to like to go there. When he visited Austin, he always go to Las Manitas. And here's John and Jeff and Fernando and me, much younger, right? And yeah, look at me. Anyway, so we used to go there and have enchilada de camarón. We all used to order the same dish, and it was very good. And so it was a wonderful time. I had one more thing I wanted to mention very briefly, just to finish. The University of Texas campus has a clock tower, like many other universities. It's very common to have this big clock tower in the middle of campus. And every time the UT football team wins a game, they light the tower orange. Burnt orange is the color of the University of Texas. And they light the tower orange when the UT team wins. That's been a long-standing tradition. I don't know when, but it's a bit more recent than the long-standing tradition. They extended this thing of lighting the tower to when a sports team or a sports person from UT wins a significant sports event. So they light the tower orange. When John won the Abel Prize, somebody from the department, maybe it was, I don't remember who it was, but somebody had this idea that they needed to also acknowledge academic, it is a university, right? So they should acknowledge, academic achievements of that magnitude. It's not the same as winning a football game or winning, but still, it's something to be. So I honestly don't. Maybe Dan Fried knows who had the idea. Somebody approached the president of the university and told me, "Look, maybe you should light the tower orange in honor of John Tate." So they had a reception for John, for the department, for all the people at the university to celebrate the Abel Prize, and they lit the tower orange, and it was very nice. I used to have a picture, but I don't have it with me, so that's it. Well, thank you very much, and I'll pass it on to Cristian. Okay.
Hello again. I'm Cristian Popescu from the University of California at San Diego. I was not supposed to speak today. I was told yesterday morning that I should say a few things because David Saltman had pulled out. Of course, I'm very, very happy to share my memories of John with you. Although I was not a graduate student of John Tate's, I was a graduate student of Carl Rubin's. Carl is somewhere here. I hope he still remembers me. I have to say that John was a mentor, a role model, and a friend to me for over 20 years. So I grew up in, how did I meet John? This is what I'm going to start with. I didn't meet him in Texas. I grew up in Romania. During my last 2 years of college in Romania at the University of Bucharest, I started reading some of John's work in number theory. So I started with Artin and Tate, class field theory. I read it from an illegal Xerox copy. This was communist Romania, late 1980s. And then I read his thesis. But most importantly, I read his book on Stark's conjectures that was mentioned by Henri Darmon yesterday. I didn't know at the time how important this book was going to be for my career. I mean, it really marked my career, as you will see in a few moments. And then, so the communist regime fell in Romania in 1989, and I was able to travel to the United States and, apply for graduate schools and so forth. And I started working with Carl Rubin on a thesis related to Stark's conjectures. So I have to say a little bit about this. By the way, I don't know how to give a speech without mentioning mathematics, so there will be mathematics in this speech, without my writing anything on the board, so don't run away. So the Stark conjectures that you saw briefly mentioned in Henri Darmon's lecture were the original Stark conjectures, unrefined, the conjectures over Q, as we call them today. They are extremely powerful statements, I mean, vastly unproved. But in order to get the right arithmetic applications out of them, and by that I mean a construction, a very general construction of Euler systems, and a solution, I mean, general solution to Hilbert's 12th problem, you have to come up with some integral refinements for them, okay? And Stark and Tate in the late 70s and early 80s came up with an integral refinement in the order of vanishing a billion case, okay? So there was a refinement. And the particular case of that refinement is the Brumer-Stark conjecture that Henri mentioned. So the Brumer-Stark conjecture is an order of vanishing 1 billion statement where the order of vanishing is imposed upon you by the presence of a non-Archimedean prime that splits completely in the relevant extension, okay? Carl Rubin, one of the main players in the world of Euler systems, realized that Stark's conjectures in an integral form would be a great source of Euler systems, very general Euler systems, generalizing, for example, the Euler system of cyclotomic units and elliptic units and the almost Euler system of Gauss sums, okay? So that's why he became interested in the early 90s in formulating a refinement, an integral refinement for the general abelian Stark conjectures, L functions of arbitrary order of vanishing. And he came up with this refinement. He formulated the refinement at the conference in Arizona. I was there. And I walked up to him after the lecture, and I said, Carl, if I prove this refinement in the function field case, would that be enough for a thesis? And he said, yes, that would be the first, real evidence that this refinement works. So that was my thesis problem. And for those of you who've read Tate's book on Stark's conjectures, you're probably aware that the next to the last chapter is on his proof of the Brumer-Stark conjecture in function fields. I think Barry Mazur was the one who pointed out that the Brumer-Stark conjecture, initially formulated in number fields, makes perfect sense in function fields, and it's a non-trivial statement. And Tate, with ideas, with some contributions from Pierre Deligne, proved the Brumer-Stark conjecture during his lectures at Orsay in 1980, 1981 in function fields. And Deligne's contribution there was something, a beautiful geometric construction, a Picard-1 motive, and its L-adic realizations, and the link between Artinel functions and this Picard-1 motive. So Brumer-Stark simply says that a special value annihilates an ideal class group of some kind. What Tate and Deligne proved was, in fact, that the special value annihilates the whole one motive. And when you do Galois codescent, you get an annihilation of the ideal class group. So that's the summary of that. I realized early on, and this was an idea of Carl Rubin's, that if I prove a refinement of the Brumer-Stark conjecture, then the whole Rubin-Stark conjecture for arbitrary order of vanishing in function fields would follow right away. Refinement meaning not only annihilate the ideal class group, but show that the special value of the L function is in the fitting ideal of the Pontryagin dual of the ideal class group. So I realized that I have to refine this beautiful geometric method due to Deligne and Tate. And this is what I did. So I took this one motive, and instead of showing that the special value annihilates the one motive, pretty much I showed that it is in the fitting ideal of all the L-adic realizations, including the p-adic realization of the one motive. And so fast forward, this was my thesis. I was invited to give my first lecture ever at an AMS meeting at the University of Vermont in 1995. John had been invited to the meeting to be awarded the Leroy Steele Prize in Mathematics for lifetime achievement by the American Mathematical Society. He was in the audience at my lecture. It was a 25-minute lecture. My first lecture, remember, I had never spoken at a conference before. I had no idea who John Tate was. I mean, I knew who he was mathematically, but I didn't know what he looked like. He was in the audience. I was looking at him. I was talking to him, in fact. Yeah. And so I finished my lecture. I was very relaxed. I didn't even know that Stark was in the audience, by the way. So I finished my lecture, and John walks up to me, and he says, "Hello, I'm John Tate." So who the hell knows what I said? I mean, I don't remember what I said, but I have to say that he was so generous with his time. I mean, I spent a lot of time at that meeting after the talk. He showed a lot of interest in my tiny thesis, and he talked to me, and he asked me questions and so forth. We spent a lot of time in Vermont. The generosity with his time, with his ideas. And so I went back home, and I started really, he urged me to write up everything. I started working on my thesis. And that fall, I moved to the IAS for 3 months. And we exchanged a lot of email messages. I found a gap in my thesis, which I fixed after a week of no sleep whatsoever. I was sleeping in the social sciences library on a table on the lower floor. The table is still there. I'm at the IA, okay? I fixed the mistake. I came up with a manuscript. I sent it to him. I started applying for jobs. He wrote a thesis. He wrote a good letter for me. I haven't seen the letter, but I suppose it was good because I had offers. And then in January of that year, I received a message from him saying, one line, job at UT Austin, ? John. Of course, I mean, yeah, so that would have been my dream job. Unfortunately, so I had received an offer from UC Berkeley, so, and I had said yes to that offer, and I asked John, can I go for 1 year at Berkeley and then come back to Texas? And he said, yeah, absolutely. I mean, he was very encouraging. Please go and hang out with Ken Ribet and company and so forth. So I went to Berkeley. Berkeley at the time was a fantastic, I mean, still is a fantastic place to be. So Ken was there, Coleman was there, Lenstra, lots of postdocs, Kevin Buzzard, Loic Merel, the students. So William Stein was there, and Jim Borger, and Matt Baker. It was a fantastic place to be. Nevertheless, I was happy to go to Texas after 1 year. I was just looking forward to spending time with John. And I have to say, I never regretted that decision. So the department in Texas, as Felipe was saying, was an extremely warm and welcoming department, especially for postdocs, and especially the number theory group that John had created there. So Felipe was there, and Fernando, and Jeff Waller, and especially John Tate. So in my second year of postdoc at Texas, Carl Rubin's book on Euler systems had just come out. I was very interested in reading the book. I had taken a course with Carl during graduate school on Euler systems, so I kind of knew what Euler systems were about. I knew that his conjecture, the Rubin-Stark conjecture that I had proved in function fields, implies the existence of a lot of Euler systems. So I worked up the guts to ask John if I could run a seminar on Euler systems. I was the only lecturer. He said, yes, but if you lecture. Okay, so, well, for those of you who are familiar with Euler systems, I mean, you know that what makes them work, what makes them do what they do, give you upper bounds for the size of a Zellmer group, is Tate-Poitou duality. So I found myself lecturing on Tate-Poitou duality in front of Tate. I was just learning the subject. This is a very, very technical subject. I was making a lot of mistakes. And John would call me out on every single one of them. But gently, I mean, I didn't, but not only that. So this is what impressed me. He was in his mid-70s. Tate-Poitou duality came out in the early 60s, so about 35, 40 years earlier. He would call me out on my mistakes, and he would come up to the board and give me a counterexample on the spot. What you said is wrong, and here is an example. So that was very impressive to me. I mean, everything was so fresh in his mind. I mean, Galois cohomology was just running in his blood. I mean, it's yeah, unbelievable. So time came for me to apply for tenure-track jobs. By the way, they were so supportive. There I got my first NSF grant as a postdoc. That's when the NSF was still a healthy agency. Under their advice and with their support, I got my first NSF grant. And then I had to apply for tenure-track jobs. It was a very successful application. John helped, and everybody helped. Carl helped. And John advised me, I had many offers. John advised me to go to Johns Hopkins. So that was my first tenure-track job. That turned out to be a mistake. Both John and I realized about 2 years later that Johns Hopkins was not the place for me. But at Johns Hopkins, two good things happened to me. I got to meet Kolivagin and talk to him about Euler systems a lot. And I got to organize a conference, a big conference on Stark's conjectures, and everybody came. John came and gave a lecture, Stark came and gave a lecture, and Carl Rubin came. And at that conference, there was a hint. I'm not going to give you names because the hint turned out to be unjustified, that somebody was trying and had a very good chance of proving Brumer-Stark for number fields. In full generality, for number fields. I had only done refined Brumer-Stark for function fields. Number fields were beyond our reach at that time. So, you know, that was one of my dreams, to prove Brumer-Stark in number fields by using the methods, the geometric methods that had worked for me in function fields. I mean, the Deligne-Tate methods. Well, in the meantime, I decided to move out of Johns Hopkins. John was very, very supportive, and I moved to the University of California at San Diego in 2003. I became Stark's colleague, And I started working on number fields quite a bit. For those of you who know Harold Stark, you know that he's not a characteristic P kind of guy, okay? So that's mildly put. So in order for me to have meaningful conversations with Stark, I had to start working on number fields. And my idea in number fields was to mimic the Deligne-Tate geometric methods, the one motive methods, in the number field setting. Of course, that cannot be done because the one motive object itself, the geometric object itself, does not exist. But what I realized is that if you do Iwasawa theory, then you can construct some Iwasawa modules that mimic the Eladic realizations of this non-existing geometric method, try to prove an equivariant main conjecture at the top of the Iwasawa tower for these Eladic realizations, and do Iwasawa codescent, and that's how you get refined Brumer-Stark, so with the fitting ideal replacing the annihilator, and from there you can get a big piece of Rubin-Stark in number fields, the so-called minus part. As Henri mentioned, the minus part means the part on which the Artin motive is acted upon by complex conjugation via -1. Okay? So this is the less interesting part of Rubin-Stark. The plus part is the one that we've never been able to touch, really, unless the order of vanishing is 1. So I started working very seriously on this. I also realized, so I want to link this with what Dustin was saying. Look, one of my favorite papers that John wrote was his paper of relationships between Galois cohomology and K-theory, K2 and Galois cohomology. That led to the so-called Quillen-Lichtenbaum conjectures, which relate the K-theory of a ring of S integers in a global field to its étale cohomology with Eladic coefficients, twisted a la Tate. And so I realized that if I do prove an equivariant main conjecture at the top of the Iwasawa tower with methods designed by Tate and Deligne, then I can prove the so-called Cote-Sinnott conjecture regarding relations between values at negative integers of Artinel functions and K-theory, Quillen K-theory. Of course, you cannot touch Quillen K-theory via Iwasawa theory, but you can touch étale cohomology. The Iwasawa modules are really Galois modules, therefore étale cohomology, Galois cohomology, therefore étale cohomology modules. And as Dustin was mentioning, I mean, there is this isomorphism that was established eventually by Voevodsky and Rost between K-theory tensored with ZL and étale cohomology. So that's how you get to K-theory. So I tried out this technique in function fields, again, in joint work with Greiter, and it worked. We got Cote-Sinnott, the Cote-Sinnott conjectures in function fields, and then I tried to apply it in number fields. In number fields, unfortunately, it worked under a hypothesis, the mu equals 0 hypothesis, conjecture of Iwasawa. So that's how we proved, Greiter and I, the refined Brumer-Stark conjecture in number fields conditionally under the hypothesis that mu is equal to 0. This was 2009. In 2009, we organized the Park City, IIS Park City Math Institute with Carl and Alice on special values of L functions. That was a very happy summer for special values of L functions. And John and I decided to drive up together to Park City from San Diego. It's an 11-hour drive. We had a grand time. We were both supposed to lecture at the Institute. He was supposed to give 6 lectures on the more classical, unrefined versions of the Stark conjectures, and I was supposed to take it from there and give 6 lectures on the refined versions. So the integral refinements due to Rubin, and a vast generalization of the p-adic refinement due to Gross, which I call in that volume the Gross-Rubin-Stark conjecture.
Did you guys stop in Vegas?
Yes, we had lunch in Vegas. But what I wanted to say is that during this drive, John and I had to coordinate our lectures. So we talked about mathematics. But once in a while, we would stop and he would tell me stories about his interactions with Artin, about the Artin Tate seminar, and also spicy stories about Lang and so forth. It was a wonderful trip. I mean, for me, it was like looking at the history of number theory through the eyes of this giant number theorist, John Tate. We gave our lectures. John was eternally unhappy with his lecture notes. I mean, you know the story. He was a perfectionist. I mean, he really wanted perfect lecture notes. And after that, we returned to San Diego. I realized while in Park City, so I wanted to mention this Tate mathematical object that has not been mentioned here before. Tate sequences. Do you guys know what Tate sequences are? They are 4-term sequences. So he introduced this in his 1965 Nagoya Math Journal paper on the cohomology of tori. So Richard Taylor is going to probably mention the cohomology of tori and Tate's contributions. So these are 4-term sequences linking, so they belong to an X class between units, S units, and S divisors in a global field. But they live in a special class in this X2, which is now called the Tate class. So on my way back to San Diego, I realized that my work with Greiter on Brummer-Stark can produce L-adic realizations of these Tate sequences very concretely at the top of the Iwasawa tower. What I couldn't prove was that they belong to the Tate class. So Tate came back to San Diego. He was working at CCR that summer. And we kept meeting in a cafe outside of CCR, and we were talking about Tate sequences, and he was trying to help, and he came up with very good ideas. And at some point, I said, John, I think we should take the adjoints of these Iwasawa modules. So the notion of an Iwasawa adjoint is a subtle notion of a duality, of a dual of an Iwasawa module that is very useful technically. And all of a sudden I hear John saying, I don't think I ever understood adjoints, Iwasawa adjoints, properly. I was stunned. I mean, I said, John, you discovered Iwasawa adjoints. You persuaded Iwasawa to insert them into the theory. Oh yeah? Who said that? Well, Iwasawa, right here in print. I showed him the paper. But this was typical John, a very, very, very modest man. I mean, and so the following year, he won the Abel Prize, which was mentioned here. I went to Minnesota, the conference, the Abel Prize conference happened in Minnesota on the University of Minnesota campus. And we were walking together on campus, and he proudly showed me Tate Hall. And I knew that Tate Hall had been named after his father, who was a physicist at the University of Minnesota. And I joked, they are already naming buildings after you. And he said, no, this was my father. You probably know, some of you know, that John enrolled in the physics graduate program at Princeton first. He moved towards mathematics a little later, I mean, maybe a year later. So he was very proud of his father's work in physics. I was also interested in physics as a young man in Romania. I mean, the reason why I learned calculus on my own in Romania was because I couldn't read, really couldn't read Feynman's lectures on physics without knowing calculus. And John knew these stories. Fast forward, 2015, 2016, I spent the year here at Harvard as a Simons Fellow. I spent time with John again. I last saw him in 2017. We had dinner at Toscano in Harvard Square with Carl and Carol and John. John was very generous. He treated us all. That's when I last saw him. And in October of 2019, I was on an on an NSF panel in Alexandria, Virginia. Samit Dasgupta walks into the room. It was very early in the morning, sits next to me, doesn't say hi. He says, "I think I got it." And I said, what have you got? And he said, "I think I got Brumer Stark unconditionally." And I started, I woke up at that point, okay? So, yeah, so I started asking him specific questions. I was sure by the end of that conversation that he had it, and he indeed did have it. And I said, Samit, we should let John Tate know about this. Definitely you should let John Tate know. John passed away a few days later. We didn't know he was sick already. He was at home in Lexington. He passed away. I don't think Samit ever got to tell him that he had proved Brumer Stark unconditionally. So I miss John and our conversations and his mentorship and his friendship very much. Thank you. I'll hand the microphone to Barry.
Thank you. It's the most moving account, and it's not the only one in this conference. The richness and beauty of Tate's mathematical ideas, they've blessed our subject. They really have done that, and our conference is celebrating that. But as you see from Felipe and from Cristian, and from everything that has preceded in our conference, there's another stratum of celebration going on here. From Mike Hopkins' moving opening remarks, through so many different encounters that are so meaningful to people, encounters with Tate. Example, including Wei Ho's mentioning that she managed to attract her 70-year-old father to number theory by the book by John and Joe Silverman. So that was personally inscribed by John. It's amazing. We're celebrating his intellectual generosity, as it is mentioned, his generosity of devoting energy, his generosity of devoting time to his students and collaborators, and the inspiring way he engaged with all of us. All you have to do is read his wonderfully personal mathematical correspondence with Serre, and that reminded me that at one point there is a climbing expedition that we had with Serre and Tate and me. I was not a climber, but Serre was the maestro, and it was a moving moment for me to see how Tate engaged with something that I don't think ever had even imagine climbing. Anyway, so John and I taught a class in class field theory. Now, John was a fundamental contributor to, in fact, one of the modern founders of the subject. And so when he lectured, he would do it with such surprise, sort of energy. He would always seem to have a kind of eureka of sudden revelation for things that he was responsible for. And he did this with the most fluent and thorough flow of exposition. I mean, it was a moment for me when I realized I have to learn from him, and I was already a professor. Yeah. But everyone has to learn from him. He mentored anyone who he came up to. I've just been to the Arizona Winter School, where there was a call for all of the mathematical, well, for all of the students and students of Tate to come for a group photo. We did this too in our conference. I said, hey, we're all students of Tate trying to get into the photo. They insisted on really official mathematical children and mathematical grandchildren of Tate. But I think we're all mathematical descendants of Tate. Here's a picture, by the way, well, I could post it later, of the multitude of students and grand students in the Arizona Winter School. Anyway, happy birthday, John.